Well, welcome. Thank you to those of you who are logging in online and those of you here in the room. We'll give it just a couple minutes for everyone to get settled and then we'll get started. Welcome, everyone. Thank you for joining us today. I'm Sarah Brewer. I'm the director of our education program at Accords, and I want to welcome you to our seminar. For those of you who are new to us, what is this Accords? Accords is the Adult and Child Center for Outcomes Research and Delivery Science, and it's supported by the University of Colorado School of Medicine and Children's Hospital Colorado. We are a unique one-stop shop for faculty to conduct pragmatic research, receive various types of services and supports for their grants and projects, and to get incredible mentorship training and education in health services research. So you can see some of the things that we do in Accords and specifically in our education program. I specifically want to highlight our partnership today with our Biostatistics and Analytic Core. Thank you for those of you who are here and who helped plan this series. Before I introduce our speaker, I want to share some of our, let's see if I can get our slides to advance. There we go. Our upcoming events. So you'll see in February, we have the next in our ethics challenges and messy decisions and shared decision making. We have Dr. Mary Politi joining us from Washington University in St. Louis. And then the next in this series, we have Rochelle Musi joining us from Johns Hopkins to talk about latent class analysis. And in March, we have the next in that shared decision-making series with a panel on health equity and shared decision-making. And the next in this series with Ryan Peterson and Dr. Katie Colborn talking about pragmatic statistical learning. Before we get started, a couple of housekeeping items that many of you probably already know, but first, if you're here in the room, hold your questions. We will have plenty of time for Q&A. For those of you who are joining us virtually, please use the chat and Q&A functions at will throughout the presentation. I'll be paying attention to those and make sure we get to ask some of your questions during that Q&A as well. And then please complete our evaluation. We'll send that link in the chat. And for those of you in the room, there are paper copies in the back of the room. That helps us make sure that you are getting what you need from our seminar series as well. All right. And then one last announcement. We also have registration open for the Colorado Pragmatic Research and Health Conference, which will be June 5th and 6th this year. And you can get registered now. Today, we have the fifth in our series, Statistical Methods for Pragmatic Research, and we welcome Dr. Jun Ying. Dr. Ying is a professor in the Department of Family Medicine. He has extensive experience in collaborative research and currently serves as co-investigator and statistician on a Department of Defense grant and an R01. He has published 131 peer-reviewed manuscripts in the areas of medicine, public, and population health. Dr. Ying's research involved longitudinal statistical models, predictive models using supervised and non-supervised methods, reliability and accuracy of diagnostic testing. He's also interested in research in missing data and multiple imputation, moderation and mediation effect analysis, and structural equation models, causal inference methods, and predictive models using machine learning. Earlier, he was trained as a hierarchical Bayesian and used Bayesian models to predict stock prices in finance markets and estimate random change points in longitudinal aging studies. Please join me to welcome Dr. Jun Ying today as he presents Missing Data and Multiple Imputation. Welcome.
Thank you, Dr. Brewer. Thank you, Dr. Brewer. Thank you, Dr. Colburn, for inviting me. So today's topic is missing data. I understand the audience could be mixed with clinicians and statisticians and people in other fields. So, the slides I'm going to present are really just try to cover the wide spectrum of the audience. I will keep it simple and practical, and to see whether we can connect it to the real world problem. My slides are a little bit long than I expected, so I may skip some of the slides. I don't think it's not a major things for today's talk. If that happens and I want to see more clearly, just let me know, or I have the slides available. You can read them afterwards. So what I'm going to do is to talk a little bit about the backgrounds, the definition, sources, patterns, and the mechanism. That's the most important thing of the missing data. And we just really quickly talk about the prevention and also briefly about the diagnosis. And then I will just move to the treatment, how to deal with the missing data problems. Certainly need to talk about the traditional method, but focus will be on the contemporary method. And I will just give the final summary in the end of the talk. So the background, really missing data problem started pretty early than most people expected in the early 1920s. And started to talk about the incomplete data by some big names like Fisher, Pearson. We have two Pearson. One is the first one is Carl Pearson, is a Pearson chi-square and a Pearson correlation coefficient. The other one, Eagle Pearson, is Lehman Pearson lemma. So those are the big names. They talk about the missing data, mainly on some issue from today's perspective, it's not that important. It's because the missing will cause the imbalanced data in each group. That will make a computation really messy. So in early days, when we don't have the computer, that's a big deal. So that's their focus point. So really, it's a big change. It's in late 1970s when Lubin talked about the missing data, and that started to create the field of missing data in literature, in statistics literature. So that's a big change. And then in 1980s, he and Little has the books and a paper come out to really establish the foundation of the modern missing data problems. Another push is in almost like 2010 and get attention by FDA So they initiate the working group to deal with how to provide a sort of guideline for the missing data problem in clinical trial. And the same thing happened in Europe too. And also Pakuri at that time also developed the guideline to address the missing data problem. So I think it's a very practical problem. Doesn't matter you as a clinician or other researcher, you probably have the experience when you submit the data. If you're doing longitudinal study or survey study or clinical trial, when you submit a paper, the chances the reviewer asks how you handle the missing data problem is getting more and more likely you will get experience this kind of situation. Same thing when you submit a grant, same if you do the longitudinal study or survey study, and the review wants you to at least propose one paragraph how you handle missing data problems. If you involved in the clinical trial, FDA may ask you, what's your plan for the missing data? And the same for the PCRI grant application. So it is a practical reason that we need to know a little bit more about the missing data and how we handle that. This is just quickly two of the big name in the missing data. One is Ruben, one is Little. And these slides, we just quickly grab from the PubMed. So you look at the left, it's really start to take off. You can see the missing data problem is start to take off almost like a late 1980s and getting to the fast track after 2000. So that's roughly what I can see from this chart. The right is, I'm just curious about other statistical topics in PubMed. And I might just do a snapshot into last year. And I could see the missing data almost like the same as other topics such as structure equation model, multiple comparison, and Bayesian statistics. Certainly you can see the machine learning and the AR are way ahead of other, but that's probably it's because too many people are involved, not just statisticians, right? You also have informatics people, and also computer science people. So that's, and plus the huge demand. So that's also, it's not surprised to me. So what is the definition of missing data? So this is from Graham, and I think Ruben and Little pretty much give the same definition. So idea is this, if you have a variable that is you are interested in your analysis, unfortunately you find some values are missing in that variable. That's the missing data. It's easier to look at it the other way. It's what is not missing data. So one thing is if you're missing observation, like one per subject completely have no value whatsoever in your data, that's a missing observation. That's not missing data. If you have a variable that is completely missing, that's also not missing data. So this is probably easier to look at from the chart, right? So the left one, Y3 is completely missing. So this is a missing variable problem. So it's not missing data. The second one in the middle, you have subject number 3 have no observation whatsoever for all the variables. That's also not a missing data problem. It's only the right one that's a missing value. And that's the one we're going to talk about, okay. Source of missing data, I will just skip it just do it very quickly. There's different sources can cause missing data. You do the clinical trial, you do the longitudinal study, people drop off or people lost follow-up, all those can cause missing data problems. And then you do the survey questionnaire. You probably some of you do the questionnaire probably have the experience too, and you find that when you receive the return stuff questionnaire, you find that not all the questions being answered, and that's very common. And sometimes you do like an instrument, like a quality of life, you find people answer, check most of the items in the quality of life, but leave some blank, and that's annoying, but that's also missing data problems. So different sources, but that's too big a topic. It's not just going to talk about in just today's presentation. What I really want to talk about that's unique for the missing data problem is one is a pattern, and a more important is a mechanism. Okay, so this is a pattern of the missing data. The first one on the left, you see like a letters in red. That's usually happen in a clinical trial or longitudinal study. You can think about like a Y1 is a baseline. At a baseline, most people give the numbers, so you don't, the chance you have a missing is very small, right? But Y2, let's say it's the first follow-up, you'll start to see some missing. And could be some participants already drop off from the study. And the Y3, that's a second follow-up, you have more, and the Y4, the final follow-up, and then you have the most. So that's what we call a monotonic pattern. And learn the second one, probably it's more common in the survey questionnaire, and you find that like for some question you get all the answer, but for certain domain or group items, and you find that there's all missing. So we call the unit to no response. And the third one probably it's a more common issue. Now, really in the real world, it's not that clear cut. It's probably all mixed, all those patterns together, right? The final one is, it's not going to talk about in today's topic, but it's interesting. It's on purpose. It's researchers design. So you design in a way to make it a missing. I'll give you an example, like I did a disease activity in children rheumatology before, right? So there's disease activity measurement instrument, and the European has their system, and Europe have, the United States have also have their own measurement, and some other place may have their own measurement. So if you survey to the rheumatologist around the world, very likely you will give the European their system, and give the clinician in the United States use the US system called a slightly European, it's called BILAG. So that way, one is more likely you get a response. The other is also save a time when they complete their survey. Mechanism, some plain word, it's called type of the missing data. That's also very important. That is originally from Lubin's book. And so probably you know there's a name such as missing at random, MAR, missing complete at random, and missing not at random. Those are the important concepts because they decide like what kind of strategy you're going to deal with the missing data. So missing at random, put something simple is I have one variable missing, but that missing could be related to other variable, other data I collected. Give an example, like you ask people to report their symptom after treatment, and for some reason you find that like an older patient are more reluctant to report those symptoms, and then the younger people. So that's a typical missing at random problem. Okay, and the missing complete at random is just a lottery. You have no control whatsoever, have nothing to do with other data available at all. I'll give you example is, let's say you do the weekly survey in your clinical trial, just have the patient to report their improvement through the computer, because some of the remote area people may not be able to come to the clinic. You do the weekly, right? For some reason, there's a bad weather, so the internet is off and the electricity is off. So the participant will not be able to give you the report for that week. Not only that, it seems getting worse and sustained for 2 or 3 weeks. So you may have the missing for 2 or 3 weeks. But that missing is completely at random because it's not something you can control. It's just weather, and you'll not be able to predict that will happen, right? So that's a complete at random issue. Missing not at random, the favorite example is like income. You ask a participant to report your income, your real income, and you may end up with find some people don't give you the income. It's missing, but those people maybe have the high income and they don't want to tell you or tell other people about income. So the missing is related to income itself. Okay. So I will just give you some example, just quickly demonstrate, see what I really mean about those mechanisms. Let's say I'm the only one have this complete data, and for simplicity, I just have a 2 variable, x and y. And I will just make the missing happen to y itself, okay, not the x, just for simplicity. So I'm going to take out the 3 numbers from y. So how I'm going to do that? I have 3 strategies, 3 scenarios. The first one is I just pick the lottery. Okay, certainly it's not a flip a coin, it's not 50 chance, it's really, in this case, it's a 25% chance, but I still can do that. I can do the lottery and then I remove these 3 people. I'm adding the 1 column called R. R means missing. And if I see missing, I code as 1, otherwise I code as 0, just for convenience, so I know the missing rate. Okay, so that's just missing complete at a random case. The second scenario is I'm looking at my X, and I'm just decide to say I'm going to remove all the Y who has the 3 largest X. So you see this chart in the bottom, the 3 people has the largest X, 15, 16, and 16, and I just remove them. So my removal, really, the decision is based on the X, other variables. So this is missing at a random situation. The third one scenario is the last column, last table is missing not at a random. How I'm going to do that, my decision will be this. I will look at Y, and I've just taken the 3 largest 3 individuals who has the largest Y. And then I would just remove those Ys. That's missing not at random. You can see I'm the only one have the first table, and then I give you the rest of the table. And I'll say, that's your data, deal with that. So your challenge will be, I need to figure out which one is which, because otherwise my strategy will. And you find that if I get the last one, the last data, the one on the right, that's the most tough one, because I don't even know the largest number removed. And I make assumption that could be the case. I still don't know what the number, because it's very hard to recover. So that's a mechanism. How bad is the missing data problem? I actually talked to some people, and many people give me the response, actually the second one. oh, you have a missing data, so you have a smaller sample size, so your power it's a factor. You get a. It is true, however, it's really not a major concern. The biggest concern is a biased result. I'm going to show you in the next slides. Bias is bad, right? Because you essentially tell people the wrong conclusion, and people will be misled by you. In addition to that, also some computation problems. So that's how bad the missing data. So let's go back to the previous example, and I'll show you what the result, right? So I'm the one holding the first table. So that's a full data. So whatever I get is the real number, so the true number. Again, we focus on Y, right? So I take the average, you find the average is 12.83. That's a real number, the true number, keep that in mind. So then we look at one by one, right? So if it's a missing complete at random, I just do the lottery. What will happen is I still get the result pretty close to the true value, okay, 12.87. That's actually is what we call the missing complete at random is whenever missing is missing, you just do the rest of the things. The good part is chances you still get an unbiased result, okay? But you look at the rest of MAR and missing not at random MNAR, you find if you do the average, it's 12 or 11.22. Way below 12.83, the true number. So that's the biasness we're talking about, and that's a concern coming from. And whatever is for when people talk about the missing data, I think the key word is a biasness. Keep that in mind. How to prevent it's just like a patient, right? So you have a missing data, you have a problem. How to do that? The first reaction as a clinician will say, well, prevent it. You need to do something right before it's too late, right? So I'm not going to give the detail because this is really just from Little's New England paper, 2012. So I think to me, it's very useful information. So you need to do something in your design stage, and you need to, the next table is you need to do something when you conduct the clinical trial, meaning before you collect the data. Once the data is collected, data is logged, and that will be going to the statistician and the data manager. That will be too late. You cannot go back to rewind anymore, okay? But that's not something we're going to talk about in today's talk. My talk really focuses on when it's too late, when you have the data and how you're going to treat that. And that's certainly also what Lubin and Little idea is how you deal with that from the statistical perspective. Now, after prevention, next things we talk about how to diagnose, right? Because we may have a different mechanism, different type of disease, and you need to figure out what kind of is the disease. That's a bad news because really, so far we don't have a good tool to talk about how can you tell the difference among MCAR, MAR, and MNAR. In particular, you cannot tell the difference between missing at random and missing not at random from the data perspective. Conceptually, you can still try to convince people, but just from the data, it's very hard, okay? Little had a book and a paper to talk about a test to tell whether it is missing completely at the random. That's the best we can get. And people also do the t-test, some simple test to tell whether there's a possibility that's missing completely at the random or not. When you say or not, It could be MAR or it could be MAR. You still not be able to differentiate. So here's just a quick example. Say so-called t-test, right? So I have a data, I have a 3 variable X, Y, Z, and let me focus on Y just for the demonstrate purpose. And Y you can see have a missing, and a missing in the last column I call 1, and if it's not missing in Y, I call 0, right? So the last column really say, okay, I have 2 groups, either 1 or 0. And then I can look at other variables such as X and Z. I can calculate their means in each variable, and I can do some t-test. The idea is this. If statistically significant, that means association. That means X is associated to the missing in Y. If it's not significant, that means no association. That means a variable such as Z, it's not associated. So in this one, interestingly, you get a tough situation. Your X is associated. That means X is not completely missing complete at random. That means your Y is not missing completely at random when you look at when you do the analysis with X, but Y is missing completed at random when you deal with another variable Z. What do you do? In the reality is, if I have this kind of situation, I would just treat as missing, not missing completed at random, right? But otherwise, I'm going to get crazy. But at least our t-test will give you the preview, say, well, your data has a situation whether the situation is missing complete at random. Unless I see all the test is not missing complete at random, I would just do the whole data as not complete at random. Otherwise, it will be hard for me to do that. Convince me, say, I do something missing at random, the other thing missing not complete at random. Completed at random. Another test is a Little's test. A Little test really give like a global, a general of the entire data, whether it's a situation missing complete at random or not. The idea is this. First of all, you need to look at the data, make it to figure out the patterns. Like in this particular one, last column, I've found 4 patterns. I code as a 4 if no missing whatsoever at all. And I code as a 1 if Y, Z and Y are missing, but not X. X never miss, right? 2 is I will code as Z is not missing, but Y is missing, something like that. So I have 4 patterns. So you can think about 4 patterns, it's like a 4 local district. And then you have the entire city of, or metropolis of Denver, that's the entire center. So the strategy is this, for each pattern or local, you find the center. And then for the entire area, entire data set, you find the center too. You compare the distance between your center to the global, and to see whether overall the distance is large or not. So that's the idea for Little's test. If the distance overall is not big, intuitively it's missing missing completely at random. Otherwise, something wrong, so it's not missing completely at random. It could be either MAR or MNAR. So in this particular case, you get a score, the distance, and it follows the chi-square test. You do the p-value, you find a significance. So that says it's not missing complete at random. Okay, again, keep in mind, it's not a complete story. It's not, then what? whether it's missing at a random or not, or missing not at a random, you still not be able to tell. So that's imperfect. Okay, so that's how much I can say about the test, okay? And then we move to the treatment. So how we're going to treat the missing data. Now let me start with the traditional method. Now certainly all those traditional methods are losers. They are not, it's going to be solid anymore, but unfortunately, believe it or not, people still doing that in their manuscript or in their analysis. So it's better to know that we try to avoid that. Another reason is really the contemporary method really borrows the idea, lots of idea from the traditional method. It's just elaborate and make it a more sophisticated and in a more reasonable value level. So we still need to talk a little bit about traditional method. And then we'll talk about the contemporary method. So the traditional method, I would just focus on two strategies, right? It's a straightforward. When you have a missing data, what do? One is I pretend I don't see it, so I delete them. And then I have the clean data set and all complete. So that's one strategy. And the other one, what I do is I just put in some numbers, make it looks like a complete data. So that's just two strategies be used in the traditional method. When you talk about the contemporary method, you probably heard people talk about multiple imputation. We're going to talk about that. And also some people are familiar with maximum likelihood estimate, but just be careful when we talk about the maximum likelihood. It's not the typical one, it's a special one. There's really another big group is a Bayesian method. Unfortunately, it's too big, so we're not going to talk about the detail in today's talk. So for the traditional method, two scenarios. One is delete them, or the other is do the imputation. There's different names, buzzwords, all those kind of things. I've just quickly talk about the deletion. There's two types of deletion, listwise and pairwise deletion. And single imputation, I'm focused on mean imputation, the regression imputation, a little bit about the stochastic imputation. Okay, so deletion, actually it's quite straightforward, right? So this is just a chart. I have the data and I put on the top panel and I have two solutions. Those red means missing. So one is it's called a listwise deletion. It's just everybody has to get a red one will be gone. So you get the bottom table and you'll find straightforwardly, say, originally I have sample size 6, now after deletion, I only have 3. So immediately reaction is I have a much smaller power, which is true, right? But also it could potentially cause a biasness if you have this deletion, if you're not careful. For example, if it's missing at a random, you do this way, you will cause a biasness. We already showed in the previous table. The other strategy is called a pairwise deletion. It's essentially it's just you create a multiple data set after you delete those missing data. Depending on your use, let's say if you want to do some analysis based on a variable y1 and a y2, you just delete any missing inside the y1 and the y2. And do the same thing if you do the analysis for y1, y3, or y3, y4, right? So that's a pairwise deletion. The good news is you preserve the sample size as much as you can, available data as much as, that's good. What the things that people don't like it is sometimes you get confused yourself about the estimate. Just look at the right panel, the bottom two tables on the left, the first one, the second one. You find that both table has the y1, right? And both has a data sample size of 5. It's good. However, you see, Actually, the participants are different. In the first table, Y3 is in the table. Why in the second table, Y2 is in the table, Y3 is not in the table. So if you do the average of Y, you will get different numbers, and then you confuse yourself, say which one I should use. Same thing for the second table and the third table, the last table. I know both tables use Y3, but the final table, you only have 4 Y3 sample size. And the second table, you have 5. Again, you will generate a not consistent result. So pairwise, it's also not perfect work, okay? So this is a quite summary from my previous work. Again, the biasness is still there, the power is reduced, and you could have some inconsistent result. Then we talk about the imputation, we fill in the number, what kind of strategy we can use previously. So again, that's an example. I have the data and I make it missing. And so the, the middle one is really the real data you get. You have 3 missing in the final 3 subjects. So I'm going to fill in some number. Let's say I calculate the average from this table for Y. I get a 12. So how about I just put the 12 for these 3? That was actually the strategy people use a lot. Probably still use that. But that could be a problem. The problem is this. You look at the mean in the final table, you find that, hey, I still get the same mean as 12, right? So I didn't do anything hurting. That looks good, right? However, the standard deviation, you find it's much smaller, right? 3.62. You say, well, that's good because I have a small standard deviation. My confidence interval is smaller. And also, I'm likely to get a smaller p-value if I do the hypothesis test. But that's wrong because you make it's not from your data. It's something you did manually. So you have the control in that. And that's a cause of problem. So statistically, my simple answer is for this approach is you will later will get an inflated type 1 error. So your mistake is larger, okay? Another strategy to fill in the blanks is this, X and Y. So I do the regression. I do the linear regression. So I will just use the X from based on the linear regression. I just use the X to predict the Y in the missing part and I'm just filling those blanks. That's another strategy, which is also reasonable. How you can see in the bottom table, if you do that, your mean actually is getting improved close to the true mean, right? However, the standard deviation is still concerned. That's because you just give the number and you don't give any variability. Am I start to lose my minutes? Okay. 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 Now, some people say, okay, now I just don't give the predictor, but I give the predictor plus some noise. Can I do that? You're getting there, so it's better. If you do that, I'm not showing in the real table number here, but you can think about like for the final one, the bottom one is 1402. If you get some noise, you may get a 15, something like that, right? So you get some variability will help to reduce the artifacts from the standard deviation. However, it's still not perfect. Why? It's because you just give one imputation number once. So the standard deviation really just calculates something called within variability. But you think about if I take a little bit more time to generate another data, to generate another imputed numbers in the second data, it may not be 15, it could be like 12. So 1215 and it also has some variability. Your strategy at this moment is not counting into that into consideration. So it's not perfect. That's actually, it's later you will see that's a Lubin's multiple imputation concept coming from, okay. Now shifted to the modern, the contemporary method. So I've started with the maximum likelihood method. Traditional method really is just say everything in the current software, right? The default is a traditional maximum likelihood method. I'm going to show you in the next slides. But really, it's not good to deal with missing at random. It's good when you have a missing completely at random. The second and the third one, is the full information maximum likely. That's the one turned out to be proved to be the good one for the missing at random. Certainly also for the missing complete at random. And also the EM algorithm is another good choice for the missing at random and the missing complete at random, okay? Because we kind of run out of time, so let me just quickly say, what is the traditional likelihood method? You have a data, you can create, let's say the data follow some kind of distribution, normal distribution. And you have a two variable x, y, you can have a multivariate normal distribution. And you can use that to build a likelihood. And the likelihood is also normal distribution, right? So you have the right picture. This is 2D, but if you have the x, y, you can have a 3D picture. But you just look at it from one angle, you get a 2D, you see the mountain, and you can find the peak. And underneath the estimate and then corresponding to the peak is the most likelihood estimate, or you can call mode. When you have a symmetry, mode, mean, median, they all together. So that's how you get a maximum likelihood. And mathematically, you can just do the first derivative of the likelihood to get the mean or the mode, and then you do the second derivative, you get the so-called Fisher information. You can estimate like a variance or covariance or correlation coefficient, all those kind of things. Okay, that's mathematically attractive. However, the current building software is have to work under the assumption is the data is complete. If you have a missing data, you need to take out all the missing data. So that's a traditional likelihood method. And then we talk about the so-called full information likelihood. So the full information likelihood is this. Again, you look at the table on the left, you have a missing data. The full likelihood or information likelihood says, I will give the likelihood for everybody, not just you have the data. And if you have missing, I can still calculate it because I can still use the mean and the standard deviation from X to calculate the likelihood. So I get a full. So the intuitiveness is both complete data and missing data be put into consideration. Okay. The unfortunate thing is the full likelihood cannot, like the traditional likelihood, you do the derivative, you can find the answer. You need to use a computation method to find the answer. But because right now the computation is not a big concern, so people just go ahead and do it, and it just take a while, you will find the answer, right? So here's what I do in the right table, just show you how I do is, you just tell the computer, say, let me try different mean of X, different mean of Y. And under each circumstance, I will get the left table, get everybody's likelihood. I add them together, I will get the final column in the right table, the summarized likelihood. And then I just compare which one give me the best answer. In this particular case, you see the yellow one, that's the largest likelihood. That means your mean of X and Y under this one is the best. You find the answer. So that's the idea for the full information likelihood. Okay, certainly it's not that simple. You also need to put into consideration of the variance covariance, but it's doable. The EM algorithm is really, it's you need to repeat them multiple times in order to find the final answer. Again, thanks to the computer, and it's become a doable things, right? So the EM really have a two-step in each iteration. One is called a E step, one is called the M step. So the E step is just putting some number in the data set to make it as a complete data set. The M step, it really is find the best solution for me and also calculate the likelihood for me. So you start to put some arbitrary number like a 10 into the table, just make it complete. It will find the solution for you in the M step. And then once you have the solution, and then you go back to the data, say, I refill the data because I need to upgrade my data. So your red part being updated in the second step. And then you find a new solution. You keep going until you always check a so-called likelihood. Right now it's called a -2LL until you find the best one. And that's the idea for the EM algorithm. Okay, so here I'm just put some table showing the likelihood result compared to the true result. The true result is 12.83. You see, if I'm using the FIMO and the EM, actually get the same result, much better than the 12 in the previous, the full likelihood version. I'm running out of time, but let me just talk a little bit about the multiple imputation. The idea for multiple imputation really it's simple. It involves 3 steps. The first step, you do the imputation. The second step, you do the analysis. The third step, the final step, is you put all the analysis together. You get a final result. In the imputation part, really borrow a lot of idea from the traditional method. The only difference is you not just generate one data set, you generate multiple data sets. That's this multiple imputation coming from, name coming from. So you have a multiple data set, each data set you have the full data, so you will just do whatever you do in your analysis to get the mean, standard deviation, all those kind of things. And then you have to add them together in your final step to pull them together. For the mean, it's easy, but for the standard deviation, it's a little bit tricky, but it's very durable. So that's a multiple imputation idea. Now, in multiple imputation, you also have different techniques. Because of time, I will just skip that, those details. But just to let you see the result for the multiple imputation, that's an example. Let's say I have the missing data, I create 1, 2, 3, 5 for the multiple imputation, and I calculate the mean standard deviation. And in the final, I put them together. My answer is 12.92. So if you compare to your true mean, you find that it's much important, improved. In this table, I may mislead you, showing like it seems like a multiple imputation doing better than maximum likelihood method like a FIMO and the EM. Actually, it's not necessary. In the ideal world where you have the largest data set and these two things will converge to each other. So I don't have time to talk about the missing not at the random. I'm just going to final 2 slides. One is the sensitivity analysis. It is very important when you do the missing data because chances when you see reviews comment, they will ask you to do some sensitivity analysis. Why? The reason actually is quite straightforward. It's because you don't know whether you're dealing with missing complete at random or missing at random. So your method may be, let's say, missing complete at random because it's easy. You just do whatever software you will, boom, you get a result. Don't care about missing or not. And you will report that. But that may be wrong, they may be biased. So you need to think about another scenario. What if your data is missing completely at random? So maybe you need to do some sensitivity analysis using the multiple imputation method to compare the result to see whether under different scenario, the result is still consistent. Maybe you do something multiple imputation and assume you are missing complete at the random, but your data could be more likely missing not at the random, but you don't know about that. So you also need to do some sensitivity analysis to challenge your data and say, let's give some extreme values in the imputation and see how my result was still the same or change under the circumstance. So sensitivity analysis is an important part for the missing data. Well, I can skip that one. So the summarized, the topic is, I hope after this talk, people realize the importance of the missing data problem. It's everywhere. It's in your clinical trial, longitudinal study, and also survey studies. And if you ignore that, you may end up with the biasness problems. And when you deal with that, one of the things is try to do some sensitivity analysis, considering the diagnosis is very lack in the missing data area. And that will be all for my talk.
Thank you so much, Dr. Yang. Do we have any? We have just a couple minutes, but do we have any questions here in the room?
Thank you for that wonderful talk.
Thank you.
When you're dealing with longitudinal data, do you think about if you're imputing in terms of like at a, let's say you have 4 time points, are you going to try to impute using the information at time point 3 for everyone, or the full trajectory of an individual, or both? That's a tougher problem.
My answer to you is yeah, both. Either way will be valid, will be legitimate. And the importance is to try different scenario and see whether still get a consistent result. I didn't show the slides. It's because we have a missed pattern like a monotonic pattern, right? So when you do the imputation, I would suggest that you use that or put it into consideration of that method in the imputation, because it's really designed to deal with the longitudinal data.
Any other questions here in the room?
Small data sets. Do you have any suggestions, advice on when you have small sample size?
Answer is no. I think small data is always challenging, because it's so sensitive to a lot of things. Sensitive to missing data, sensitive to the method you choose, sensitive to the distribution. And really, there's not like a one cure for all type of approach. And I appreciate you raised this question. It's an excellent question. It's just, I think, again, I'm all based on the common sense. I will look at what kind of things could be associated to the small data problem, such as distribution. And then I will consider use different scenario for the distribution or distribution-free approach, right? And then I understand how sensitive you're missing one data in the small data, that's a big deal. So how sensitive to that probably would also be considered if I put a different numbers in this missing part, what kind of consequence it is. So it is not the easy way, but certainly intuitively people say Bayesian method has advantage, always has an advantage for the small data set. And that's why you see so many Bayesian methods being in phase 1 trial, because phase 1 is always a small data set.
Thank you. We have a number of comments online thanking you for your
Sure.
talk. We also had a couple questions about the slides. Those are already up on the Accords website. Jordan posted that in the chat, so if you are looking for those slides to review some of this information, those are already up online. Any other last questions? For those of you online, the link to our evaluation is also in the chat. Okay. Well, thank you so much, Dr. Ying. It was
Thank you.
wonderful to have you come talk with us today.